Okay, good afternoon, everyone, and welcome to Java Application Design Practices to Avoid when Dealing with Sub-100-Millisecond Service Level Agreements. So this is a presentation done in cooperation with Intel and IBM. And my name is Daryl Meyer. I work for IBM, and for the past 12 years or so, I've been working on the just-in-time compiler component of the J9 Java virtual machine that runs under many of IBM's products. I've worked with several customers on doing performance analysis. I've done benchmarking stuff, and recently I've been focusing on Java benchmark development as well. My colleague Anil Kumar is from Intel, and for the past decade he's been working on working with customers and improving Java performance on Intel's fleet of hardware. Also, with this presentation is Elena Saipina with Intel, but she unfortunately couldn't be here today, and she does Java performance as well. So we've got a lot of material that we want to cover today, so I just maybe kindly request that if you have any questions, maybe you can hold them to the end, because we do have a fair bit of stuff to get over through today. So what we'd like to do we'd like to share a lot of the insight that Anil and I have from discussing Java performance with customers that really care about response time workloads, and really impart a lot of the experience you've had developing a new benchmark for measuring Java business logic that actually uses a throughput, or has a response time component to it as well. Would like to really educate you on what really contributes to higher transaction times in transaction response times in applications, and also importantly is to figure out actually how to measure that response time as well. Because if you're not sure what you're measuring, then you might have some issues when you're trying to identify where the problems are. And then starting at the sort of the top of the stack is the Java application itself. So stuff that Java developers would actually write. And this is the thing that you perhaps have the most influence over. And there are some things that you can be doing to improving your response time. But there's also things that you shouldn't be doing as well. And I guess that's maybe more the subject of this presentation to avoid, so that you actually get better response time in some of your transactions. But looking beyond just the Java code itself, the Java code runs on top of an entire stack of components, from middleware down through the JVM, through the operating system, and so on. So to really get the best possible performance, you may want to tune different layers in that stack as well. And even if you think that you're getting a really good response time with your application, perhaps you could actually be doing better. So we'll be giving a few tips to see if there are some tell signs there that you can actually be getting a better response time. And woven throughout this, we're going to be giving lots of practical examples. And these practical examples have been derived from the new Spec JVM 2012 benchmark that does have a response time component to it. So I think there's a lot of stuff there that's relevant. So the title of the presentation mentioned service level agreements. And a service level agreement is basically some kind of a commitment to provide some sort of service at a prescribed level of performance. And there's lots of different ways or different kinds of SLAs. But the one that we're going to be focusing on mostly today is response time. We're going to touch on throughput a bit as well, but response time is really the thing that we want to focus on here. These can be informal SLAs, so things like your application must respond to a certain event within a certain amount of time because otherwise it won't function correctly. Or the other way would be if it was contractually obligated, you actually had an agreement with a customer that you needed to provide a certain service within a certain amount of time. Then, but what we're really looking at here are informal ones. But I think that a lot of the techniques that we present today are going to apply to more than one environment. Response time itself can have a number of different definitions, and as we'll see in just a sec, depending on how you measure things, your response times can actually be quite different. So really what we're talking about here, and a lot of the information that we're going to be giving today, is really in the transaction space. So really, how much time do you really need to provide to complete a transaction in a response to do that work? And in the general sense, lower response times are better. And it's really a goal that you really want to achieve if you want to get good performance and customer satisfaction as well. And with response time, there's often different perspectives that you can take on it. So for example, if you're a user and you've just entered some information and you click submit, perhaps what you really care about is that you get your data back or whatever information you're requesting within about a second or so, or half a second, something like that. So your response time is actually quite high. But if you are developing like a real-time trading application where you have to respond to some kind of a market event, then the response times in those situations are actually much, much lower, and they're probably in the order of like 50 milliseconds to 100 milliseconds, something like that. One thing that we hear from customers as well when we start talking about response time and tuning response time is, well, I have a transaction that's not achieving the response time that I think that it should be. So I think the way that I'm going to fix that is to actually just increase its throughput, and therefore I'm going to get a lower response time. While that's true in many cases, and in fact, if you actually do improve the throughput of a particular transaction, you have to be aware, though, that it will have or may have effects on other transactions that are occurring in the system as well. So, for example, you can throw a lot of resources at improving the throughput of a particular transaction, but it may come at a cost, and that you'd see that your response time on other transactions will actually increase. And then, therefore, your overall response time will actually increase as well. So you really want to keep an eye on a lot of different things there when you're looking at response time, and not just focusing on one at a time. So how do you measure response time? And it's actually a fairly simple question, but it's also one that we'll find that different customers do things a little bit differently. So it's really important to nail this down, because if you really want to focus on improving your response time, you really got to know what you're measuring and how you can influence that particular response time. So up here we have a particularly sort of contrived system where we've broken out the different components of a transaction request into different components here. So a request comes in, it gets marshaled into some kind of a request queue, and then we have after we have this transaction mechanism which basically pulls a request out of the queue and formulates a transaction and then submits it into this transaction queue. And then we've got a thread pool of some sort that has a number of threads in it that when there's an available thread, it'll just go grab the next thing out of the transaction queue and start executing it. The transactions take different amounts of time. They may complete in different durations. And then when things are done, the responses are sort of marshaled through a response or a retirement queue and then ultimately delivered back to the requester. So in a model like this, there are a few you can actually measure different kinds of response times in here. So for example, you can actually measure the response time from the time that the request is actually submitted to the time that the response is delivered. And from a user point of view, this is really what they really tend to care about. But another way of looking at this as well is measuring the response time from the time that, not from the request is first made, but by the time that a transaction is formed and it's actually submitted for, queued for submission. It's ready to run, but nobody's running it yet. And then perhaps another way of doing this is to actually, once the transaction actually does start running, measure the duration at which it takes to complete and call that your response time. So you really have to sort of narrow down here what it is that you want. These are just 3 examples, but there's other permutations here as well that we can go through. Other important things to remember about measuring response time is to make sure, and this actually happens more often than one might think, but make sure that when you're when you're actually measuring response times, make sure that the timing aspect of it is not part of the response time. So what tends to happen sometimes is somebody wants to take a snapshot of the current time, but they'll also want to log that to a file, or they want to do some tracing with that sort of thing, or send it out a socket, something like that. And often the setup for doing that extra logging is included as part of the response time. So you want to be careful that when you actually do take your snapshot of the time, you're not including anything else with that you don't want. Even though it may not seem like it's a big overhead, over time, those little little bits of delay tend to add up and may cause your overall response time to increase. Java provides some fairly handy methods for doing timing. So, and these are in the system class, so system nanotime and system current time millis. You should be aware, these are perfectly fine methods to use, but you just need to be aware that there are accuracy and precision implications of using these particular methods. So for example, system.nanotime specifies that the result that's going to come back to you is going to be some sort of a nanosecond, it's going to be a nanosecond precision. So you're going to get a nanosecond value back. However, it doesn't say anything about the accuracy of that. And in fact, many operating systems do not actually have a nanosecond granular timer that'll actually hand you back something that actually is a nanosecond. So you're going to get something, let's say that was in milliseconds that was converted into nanoseconds. So you have to be a little bit careful about the accuracy and the precision of these timers. And don't go nuts with the timers either. I mean, even though they are relatively cheap to do, if you use too many of them, there will be an overhead there as well. Virtual environments. Response time in these environments can be a little bit tricky as well. What you have to watch out for when you're measuring timing stuff on virtual environments is clock skew. So if you're running a virtual environment that's getting its clock source from the host, there might be some skew in the time. It may not actually be the time that you think that you're measuring. So if you suspect that there is some kind of a clock skew happening there, or you should suspect that there would be, then what you should try to do is to actually measure your clock source on some kind of an external system that has a much more sort of consistent timer on it. And then one example here to kind of drive some of these points home. So what this chart is showing is a bit of a sneak peek at a response time throughput curve that's coming out of this SPEC JVM 2012 benchmark. I just wanted to sort of show a couple of points on this thing to show that you really need to focus on, that you need to be aware of what exactly it is that you're interested in when you're looking at a chart like this. So what this is showing here on the x-axis are different degrees of an injection rate. So this is these are different throughputs, and what's showing on the y-axis are the response time at transactions injected at that throughput. And the way that this sort of works within the workload is that at a particular injection rate, let's say 3,000 in this case, so 3,000 operations per second, 3,000 requests per second, we're going to measure the response time of the transactions that occur in that particular for that particular injection rate. And you can sort of characterize them based on you can characterize the spectrum of them. So, for example, if you just look at sort of the median response time in that entire range. You can see from the blue, the dark blue dots up there, that's the median response time, and it actually looks pretty stable. And a lot of systems, a lot of people really only care about the median response time, and that's perfectly fine. But if you start to increase the size of that data set, the group, you're going to start to see that your response time can actually change quite substantially. So the purple ones here, the sort of violet-y, purpley ones, represent the 99th percentile. And you can see that the response time, even at 3,000 here, is actually going to be up closer to, like it's a couple of order of magnitudes larger. So if you start looking, so if you care about most of the response time of most of the transactions, then you have to be prepared that the response time of those is actually going to be maybe actually quite larger than others. So the tips and techniques that we're going to be talking about here, some of them apply well to median response time, others apply well to higher percentiles as well, like 99. So, as I mentioned in the intro there, the influences on the response time themselves is not just from the code that you write. That does play a big part of it, but when you look at the stack as a whole, there are a number of different places that you can tune in order to get really good response time. And in often cases, you actually have to look past your application. And sometimes this does work against Java's philosophy of write once, run anywhere kind of thing. But in some cases, it would make sense if you actually did look at the entire stack and tune your way down through it. And we're going to be talking about each of these different layers here as we go through this. But before I talk about that, though, I do need to introduce this benchmark because it will serve as a as really the case study that we're going to be used for a lot of examples in this particular talk. So Spec JVM 2012 is the next generation Java business logic benchmark developed by SPEC, the Standard Performance Evaluation Corporation. So this is an industry a consortium of companies like Intel, IBM, Oracle, AMD, Hewlett-Packard, things like that, that really define workloads that are really trying to encourage fair measurement of performance on systems and software and that sort of thing. And up until this point, the Java business logic benchmark has been Spec JVM 2005. Some of you may be familiar with that. But we've come to the realization that that particular benchmark isn't really addressing a lot of the needs of users these days. It doesn't have a response time component to it. It isn't using modern features of the JVM that customers are doing. It's not structured the way that that customers like yourselves are actually writing code. So we decided a few years ago that this needs to be revamped, and we actually rewrote the entire benchmark to make it much more relevant to customers and for the next 5, perhaps 10 years with this workload. The good thing about a benchmark like this is that it tends to drive a lot of good stuff into hardware, and it tends to drive a lot of good stuff into software. It forces JVM vendors in particular to innovate on key technology that would actually benefit everyone. And so that's really one of the focuses of this kind of workload as well. The business model of this workload is a supermarket supply chain. So we've got headquarters, we've got supermarkets and suppliers and customers buying things and customers returning things and buying stuff online, that sort of thing. It's a transactional workload. It's very scalable. There's multiple ways of that this workload can actually be configured. It can be run under a single JVM. It can be run with multiple JVMs. It can be run with in a distributed mode. And it's also self-injecting. So it basically figures out on the system that you happen to be running on, be it a small system or a very large-scale server, it figures out how much work that system can do, and then sort of tunes itself to inject just the right amount of work on that thing to try to test it and get it to fall over. And it forms the workload from that. It does use very customer-relevant technologies, very modern stuff. So a lot of Java 7 features. It uses Java util concurrent fairly heavily, XML stuff, security, which is really lacking in a lot of benchmarks. And so hopefully this is going to cause us to do a lot of innovation in this area. And then perhaps the key thing as well that differentiates this from other spec workloads as well is that it actually has 2 metrics, of one of which uses response time. So it has the sort of more traditional throughput operations per second, but it also has a response time component as well, which is good. And like I said, we're going to be using this as a case study in this presentation. So starting at the top of the stack is your application, and the way that you write your application, and some of the ways that you can design your application. So really, in order to improve response time, one of the things that you really want to be focusing on is reducing the amount of latency that you have in your code, and because you really want to try to minimize as many pauses as you possibly can there, because that just works against you for response time. So one of the first things that you want to think about is making sure that it's actually scalable, and there's a lot of code out there that's not. And scalability, by the way, what I'm defining this as, is really the ability to increase throughput as you apply more resources to something. So, for example, if you happen to be running your application and it's running fine on a little 4-core processor, and all of a sudden you run on the latest, Westmere EX that's got a 10-core processor there, do you see at least a 2x speed up? Do you see any speed up at all? And if you're expecting to see a speed up and you don't, then that might be an indication that your application really wasn't written that way. So really what you want to be doing is to look at your application and whatever software you're writing and make sure that it's prepared to run on modern hardware. Because hardware these days, it's starting to see more and more cores. It's scaling horizontally. It's not necessarily, it's not scaling vertically by throwing more, gigahertz at it. you're really going to really take advantage of the hardware, you're going to have to start writing code that actually does take advantage of, you know, the multiple cores. This isn't necessarily possible in all cases. Depending on your application, depending on your problem domain, it may not be something that's easily parallelizable. So it may not be something you can do. But you do want to look at creating more parallelism in your application. To help you with this, Java, the JDK actually does provide some help for this, and this is in the form of, in the Java util concurrent package, you know, there's a task executor framework for very large tasks and managing those and having those tasks completed and sending responses back. And Java 7 actually introduced much finer grained parallelism in this fork join framework for doing task decomposition. So you want to look into those. And I've already mentioned the Java util concurrent package, but if you've never looked at this before, and there actually is a lot of customers out there that haven't even heard of Java util concurrent before, not even aware of what it can do, I certainly encourage you to look into this because it's a very, very useful package in the JDK. And it was actually introduced back in Java 5, and there's been sort of incremental improvements made to it in Java 6 and Java 7. And really what this is, it's a very rich set of building blocks for helping you develop scalable applications. And it's got a lot of cool stuff in there, and it does a lot of the hard work that some people try to do themselves, but they just don't get it right. So for example, if you want to write your own kind of funky lock, or if you want to do, you know, if you want to do your own concurrent collection, you can try that, but in a lot of cases you may have some bugs in there. It's very difficult to get it right to satisfy Java's memory model and threading model and that kind of thing. What this package basically does is takes care of all that for you. So you've got things in here, like I said, it does a really good job with concurrent collections. It's got task management stuff. On fields, it does, there's operations that you can have on, like atomic operations and fields. Those are pretty cool. Really want to encourage you to use Java util concurrent as a base class for new stuff that you happen to be developed. So don't write your own stuff, but you can write it on top of this. Extend the collection classes, for example, and take advantage of a lot of the underlying features here. And perhaps one of the best reasons to use JUC is that it is actually optimized pretty heavily by modern JVMs. There's actually some operations in here that you don't actually see as a developer, but actually the way that these classes are actually implemented, that JVMs can basically take and in many cases just transform into a single instruction on a particular architecture. So really want to encourage you to use this because we can do a really good job optimizing this. Another thing that sort of stands in the way of increasing or decreasing your response time is extra synchronization. And you know, this is necessary. I mean, Java is, after all, multi-threaded, so you are going to need some synchronization there. But you want to make sure that you don't have excessive synchronization, and you want to get rid of anything that's not really necessary to have. Java traditionally has got some fairly heavyweight synchronization, as I'll call it. It's the synchronization that's built into the language, you know, with the synchronized keyword and monitors and that kind of thing. But unfortunately, that kind of synchronization does inhibit scalability, and it is in some cases difficult to work around. It is useful to use that kind of synchronization when you really do care about mutual exclusion. You got to keep all the other threads out, but there are lots of cases where you can actually get better performance by bending those rules and relaxing those rules a little bit. JVMs can help you here. We do try to recognize when you are, when there's redundant synchronization and eliminating them, but you certainly shouldn't rely on the JVM for finding these opportunities and getting rid of them. JUC is maybe where you want to consider when you're developing your own locking, for example. You want to start looking at things like this, or it's got a much finer grained lock, and it also provides building blocks for putting together your own locks. So there's some cool stuff there. Contended locks are another problem. So if you happen to have multiple threads that are all trying to get the same lock, then you may have a problem because the ones that don't get the lock have to do something. And in many cases in the JVM, the Java runtime is basically just going to put those threads to sleep eventually. And that's not good for your response time either. If your thread is basically sleeping instead of doing work, it's not helping you. And sometimes you don't even need synchronization at all. You want to look into using volatile fields where it makes sense, because volatile fields really use the Java memory model to enforce, the ordering of certain operations. So these are very useful for things where for example, you have one writer and multiple readers. You may get away with being able to use a volatile field in that case, which doesn't end up using a lock, but has pretty good synchronization characteristics there as well. You want to avoid excessive object allocations, and we're now starting to get into the point where garbage collection is starting to come into this discussion. And really, the more objects you end up creating, the more strain you place on the garbage collector. And while it may seem that you may not be creating a lot of objects, in practice your heap can actually grow quite large. And it does have, and we'll see some examples of this shortly, it can have a fairly negative effect on your application, and in particular, your response time. If you can, don't put allocations in loops unless you really need that kind of a semantic. Try to share the same object within the loop and hoist the thing out of the loop, the allocation out of the loop. Consider using weak and soft references when you can. A weak and soft reference, or a weak and a soft reference, if you're not familiar with those, is basically a reference that's not really strong enough to prevent another object from being garbage collected. So, for example, if you have a weak reference that's the only thing that's pointing to an object, that object can still get garbage collected. It's not like the sort of traditional way that the garbage collector works, where it looks around the heap and tries to find references to objects. If it finds a reference from one object to another, it still assumes that object is live. But if the only thing pointing at an object is a weak reference, for example, the GC can still get rid of it. In fact, it will on each cycle. Soft references are exactly like that, except that they tend to persist for a little bit longer. They have a little bit looser rules on when they must be cleaned up. So if you haven't ever looked into weak and soft references before, please do. Where they're useful are for caches. In particular, where you want to keep some information around that, let's say, isn't being written a lot, or you just want to keep something close by, you can use weak references for that. If you want to supplement information about an object with sort of a side table of some sort, you can use weak references for that. Any place you can easily rematerialize the data. If you don't care that if I ask for some information, it comes back as null, and then I can recreate that data, fine. This might be something you might want to look into. Another thing you want to keep an eye on as well when you're talking about object allocation are immutable classes and some of the side effects of using immutable classes. So for example, Big Decimal is a good example of this, where it's an immutable class, but it provides a number of operations like add, multiply, subtract, things like that. But the interesting thing about those is that every time you do an operation, you're getting a new object back. So if you tend to do these in loops, or you have a lot of this code, then you're going to start to see a lot of Big Decimal objects being created. So just beware of immutable classes and the side effects that they might have. Okay, so into some real data here. So I think I have to preface this data with some information about how we actually obtain these. So when we looked at measuring certain things to basically present here, we're looking at a benchmark that's been the application itself has been tuned quite a bit. Like, we had lots of problems early on while developing this workload with thread pools and numbers of threads there. So we ended up fixing a lot of those problems. And in terms of caching data and that kind of stuff, we fixed up a lot of those issues. So what we're really seeing here is whatever's left. And what we're going to see from a lot of these examples is whatever's left often has the finger's often pointing at the garbage collector. Not always, but it also often shows there are interesting characteristics in the curve that point to garbage collection. So what we're looking at here is an example of accumulating too much data in your workload. And this is talking about receipt storage in the benchmark. And what that really means is that the way that this particular benchmark works is that when a supermarket completes a transaction, it sends a copy of the receipt to its headquarters for storage for some reason. I mean, it's there at the headquarters for archiving or whatever it happens to be. But the point being, though, that it's actually sending something over and over, and this list is ending up growing quite large. And what we're showing here are two different response times that we want to care about. So we're looking at median response times for the transactions, and we're looking at the 99th percentile. And what we did here was we basically varied the number of receipts that we end up storing in the headquarters for processing later. And what we can see from the 99, the top chart there, is that as we increase the number of receipts that we end up retaining, the median response time doesn't really change all that much. But there is an impact on throughput. The x-axis here, the JOPS, is actually the throughput. So the farther you go to the right, the more throughput you actually are able to achieve. But if you look at the 99th percentile, as you increase the number of receipts being stored, you can see that 10,000 receipts is okay. 50,000, you're starting to get a little bit of bumpiness in your response time. A few spikes there. But if you all go all the way up to 100K, your curve is starting to get pretty spiky there, and a lot of that is due to garbage collection and just the way that it actually has to spend time cleaning up those receipts that are no longer needed anymore. So it does have a fairly big impact on the 99th percentile. But if you only care about the median stuff, it looks decent. Another example here is another component of the workload where the headquarter component is able to do mining of some data that comes into it, and it can actually use this data to influence the benchmark. So, for example, it can figure out customer buying patterns or which products were purchased together, and it can use this information to influence future purchases by customers and that kind of thing. What we found when we were developing this workload was that the amount of work that we gave the headquarters to do, the amount of data that it had to crunch through to do this data mining, had a fairly significant impact on performance and on response time. And in the median response time here, as we decrease the amount of work, the blue line here is a decrease in the amount of work. As we decrease the amount of work that the headquarter had to do, the response time, the median response time didn't really change all that much. But if you look at the 99th percentile, and unfortunately this graph is a little bit clipped here, but the response time for the 99th percentile actually had some fairly high spikes in it. It starts to get fairly spiky there at the end. And you don't see how high those go, but if you look there, the peak there is now 1,000 milliseconds. So some of those pauses, some of those response times are actually taking well over a second. So you definitely want to keep some of those things in mind. Another aspect to look at here in your application is to reduce the overhead that there is to access data. And this is a very common issue in client-server workloads. And a very, very common way of getting around this is to basically cache some data locally on a certain system to avoid actually having to talk to somebody else to get data. And this actually is a fairly useful approach, especially if your data isn't really going to change that much. But you have to be careful with this, right? Because if you start to cache too much, then again, you're going to start putting pressure on your garbage collector. And this is also an example of where if you cache too much, you can do a really good job improving the performance of this one thread by caching all his data, and he's like zipping along, getting really good response time. But if that's now causing garbage collections, that could actually be harming other threads as well and eating into their response times. So you have to consider the system as a whole and not just necessarily focus on single transactions. You have to look at the bigger picture. Other ways that you can actually reduce your data access latency is to use Java New I/O, so introduced in Java 1.4. And there's lots of cool stuff in Java 1.4 for tying Java I/O closer to the operating system and some of the features that the operating system provides. So, for example, things like buffering and channels and selectors and that kind of thing. So it actually does tend to leverage a lot more of the performance of the operating system, kind of gets it out of Java and lets the operating system do its thing. So use that if you're not using it. And another thing that we really found while developing JVB is, in terms of your data structure choices, if you choose blocking data structures, so if I come up with a queue of work and it's a fixed size, it's got 100 elements, let's say, and if anybody else tries to add, you can add elements up to the point when it's full, but if anybody else tries to add, it sits there, puts up its hands and blocks. That wasn't really good for response time either, because your thread isn't doing any work. It's just sitting there waiting to add something to a work queue. So the way that we worked around that is to sort of structure it such that we could get away with using non-blocking data structures. And the Java util concurrent package does provide non-blocking data structures as well. So, for example, I've got up there concurrent linked queue, so you might want to look into those as well. You got to be careful with those though, because again, you're going to get into the point where you don't want to accumulate too much data, but just so you know that it's there and something you want to look into. So again, back to JVB. This is an example of a supermarket caching some data so it doesn't have to talk to the headquarters. And the example in this particular case here is it caching information about customers that isn't likely to change, his name, his credit history, and things like that. It keeps a bunch of information close so it doesn't have to do the talking all the time. And as you can see, as you increase the amount that you cache, the throughput really increases. And if you're just looking at the median response time, it doesn't really have that much of an effect on the median response time. But again, if you look at the 99th percentile, you start to see that keeping more and more data local is starting to incur some fairly large spikes there at the 99th percentile, which may be unacceptable to you. So you do have to kind of tune the amount of data that you're retaining there, or look into ways of fixing your garbage collection or tuning your garbage collector in order to get decent response time at the 99th percentile. So these days, many Java applications are not written from scratch as sort of standalone entities. A lot of them are, but many of them are not. And oftentimes you're built into like some sort of an app server, or you're using a lot of third-party packages, or you're using like some Apache stuff. And really, the message here is that if you're developing with other packages or on top of other frameworks, you really need to understand what they're doing as well and how they could possibly be impacting your throughput and response time. And there isn't really any sort of very specific advice that you can get, but the more general advice, depending on the package, is to really understand how those packages are using thread pools, how they're doing thread management, how they do caching, how they do connection pooling, things like that. And then understand how to tune that for your environment, for your application, to get the kind of behavior that you need. Next layer below is the Java virtual machine. And it's a fairly important layer. It tends to, it does run everything. And there's lots of things that you can do to improve your performance, lower your response time by tuning the Java virtual machine. This is just sort of a typical example. This is J9's internal kind of structure. It's a very layered kind of approach. And it's typical of JVMs these days. But it's the point here being that it's fairly complex. And there's lots of little areas in here that you can use to tune. But I'm going to focus on the most important ones. And the most important one is garbage collection. And especially when we're talking about response time. And it's been something that since we've been developing the SpecJVB 2012 workload, the theme that comes up, it's been coming up for years, has been garbage collection and how we need to tune garbage collection in order to attain the response time that we want. This is worth a presentation on its own on garbage collection tuning. But really what you need to do is to understand what your application is doing, understand what your application is doing with its data to decide what kind of a garbage collection policy you should be choosing for your application. And oftentimes you are trading throughput versus response time. And And the thing that tends to work against most applications is the fact that when the GC does do work, most GC policies have what they call stop the world phase, which means all threads have to stop while the GC does a little bit of work. And that really kills your response time, for sure. So what you want to try to do, if you really care about response time, is to try to minimize these stop the world pauses that happen. So there are a variety of different kinds of garbage collection policies out there. And so, for example, throughput ones are ones where you really don't care about response time that much. You care more about doing a maximum amount of work. You can incur longer pauses, you can incur longer pauses when the garbage collector has to kick in, but you really want to get a lot of throughput done there. Most GC policies these days are concurrent, which means that the garbage collector actually does a little bit of work while your application is running, such that when the garbage collector does kick in, it doesn't actually have to do as much work as it would have if it wasn't doing that work in concurrent. And what this tends to do is to lower your average pause time for garbage collection. That's good for response time. These days, we're starting to see more and more balanced policies, which, they tend to that carves your heap up into regions. It improves parallelism. It goes after collecting areas that have got the most garbage and that kind of thing. So I think that that's going to be sort of the next area where garbage collection is moving into, and where we're going to start to see some innovation there. Another message here is to actually tune your heap parameters, the maximum size, your nursery size, your old space size, that kind of thing. A lot of that is really dependent on your application and how it's using data again. But JVMs are getting better at doing this automatically, but to get the best possible results, you still want to do that yourself right now. And there are verbose logging features available to help you correlate what's going on in your garbage collector with what's going on in your application to see if, I got some issue with my response time here. Maybe there's some GC event that's causing that. So just a couple of quick comparisons here of performance using different garbage collection policies. So this is basically a comparison between a concurrent mark approach and a non-concurrent mark approach. And as we can see, the one that sort of favors throughput actually does get better throughput in the median response time. And the response time isn't really all that different in the median response time. But if we start to look at the 99th percentile of transactions, you see that the more throughput-based policy really tends to, again, it has better throughput, but there are often some huge spikes that are occurring there when the application has to stop and pause. And if you really care about not having really big response times, this is going to kill you, because you can see that some of them are well over 1 second there. But if you look at the concurrent mark one, the performance is much more stable, much more predictable, and on average, it actually works out better for response time. These days, most systems are 64-bit. And more and more applications are starting to take advantage of the larger address space, and so we often see this with in-heap databases, in-memory databases, grid kind of applications, things like that, and that's fine. I mean, it's great to use that sort of thing. But the one thing to keep in mind with 64-bit architectures is that they're not as efficient as 32-bit in terms of utilizing your system. And the reason is that Java is a very object based system, and representing 64 bits is a lot less efficient than 32 bits because your pointers are twice as wide. You're getting less utilization out of your processor caches. You're getting less utilization out of your memory, and that's starting to stress the hardware. So JVMs these days have a solution to that, and what they basically do is to say, well, we can actually represent up to a certain point. We can actually not use 64-bit addresses. We can actually just use an offset into a certain memory range. We can have it as a 32-bit offset. And so we can get all the sort of space benefits of 32-bit, but, the pointer space benefits of 32-bit, but at the cost of a little bit of runtime overhead for expanding that offset out into a real address. And that can be enabled with either using compressed OOPS. You may have heard of that before. So that's something you want to consider when you're using 64-bit. And if you are running with probably less than a 30 gigabyte heap, something like that. I don't have data on that particular. I don't think I did. No, I don't. I don't have data that actually shows that, but just sort of empirically, what we tend to see with some applications that your throughput is going to increase by about 10 to 15% if you use compressed OOPS, and your response time may increase by something like 5%. That's what it did in Spec JVM 2012. The next layer here is the operating system, and there's a couple of things I just want to point out here. So one thing that is particularly good for performance and good for eliminating bottlenecks in your in transactions these days is to optimize the memory that's actually being used. And where that, so most, well, actually all operating systems these days use some kind of a paging approach. And when you have a virtual address that's being mapped to a physical address, the processor internally uses these things called translation leukocyte buffers to help with that translation, to cache the effect, to cache that translation. And that buffer is actually affected by the size of the pages that you use. The bigger pages you have, the more reuse you can get out of those buffers. So what we like to see is, if the operating system allows it, is to use larger physical pages. So for example, going up from the standard 4K page in a lot of operating systems up into the 2 megabyte range for a particular page. So if you tend to use a lot of data, you can actually reduce the overhead of accessing that data by using large pages. And you have to enable these in the operating system, but to use those on the command line of the JVMs, you specify that you want to use large pages. And just a quick effect here of what happened on JVM 2012 is that when you enable large pages, throughput does increase. Median response time again doesn't seem to have much of an effect, but again on the 99th percentile, the larger pages, while you're getting more throughput, it's trying its best to keep the response time down as much as it can there. And the last 2 points that I want to mention here are about thread scheduling. So you do want to keep your eye on context switches, because if your thread isn't running, then it's not doing anything, right? So that's just eating into your response time. And there's a couple of different flavors of context switches. There's sort of voluntary ones where you give up the processor yourself. You're saying, I'm going to park my thread because I'm contented, for example. There's a contented lock here. I'm going to give up I'm going to park my thread. That's not necessarily good, because you're giving up. And involuntary ones, we actually had this problem with this particular benchmark early on, where we had too many threads, and they were causing, and each of them wanted to do work, and they were causing other ones to be constantly swapped out. So if you have too many threads, you're going to want to keep an eye on that. And then maybe something that actually Neil's going to show a little bit of data on this in a bit, but you want to watch out for threads moving around. If you're running on one core, then it's not, and he's happily accessing his data on that core, it's not really good for performance. If you suddenly switch to another core, the OS schedules you in another core, and you're doing remote access to your data, and that's just going to cause extra latency there. So you do want to watch out for that. Use the facilities in the operating system for looking at thread migration. Okay, so that was covering most of the software stuff. And Neil's going to come up and talk about the hardware itself and different aspects of that.
Thank you, Darren. So I'm the hardware guy, and with that, I do want to ask one quick question, that when we are dealing with 100 millisecond or lower response time, most of the time you might have to know your hardware. So my question is, most of the time what I have seen in the customers, you're programming, and in that space, you really don't care for the hardware. But at that lower response time, you go 100 millisecond or 10 millisecond, there is not getting away from the hardware part of it. So how many people do really know their hardware, where the thing going to run? Some idea? Pretty good. At least I knew one hand will come. That is Gil from Azul. So I think on the hardware space, that could be one whole presentation on each of the topics once you go in the detail. And particularly I have seen those questions when we are talking about sub 1 millisecond response time. But I do want to highlight quickly the things we have seen very often, like for example, power management. Most of the time it works very well. You will not see an impact. But if you have a financial or the high transaction type response time, and you are at very low utilization where the response a request could come, you need to quickly do the work and go away, you could see fairly long latencies. And in those cases, people don't like to leave the power management enabled, though there are trade-offs. So you do want to aware at a high utilization, it's not going to make a difference, but if you have any phases of low utilization, you could expect some strange behavior. So you may want to check, is that causing it? The other ones, I will not go in detail about the physical memory, or if you have memory swapping, very common space, you could see long latencies there. They won't be from GC, but you could watch it by using your operating from OS level monitoring itself. Is it memory? Same thing for the network. For example, you could have, we have even in this application, if it's a two-tier application where the request is going through, if you don't have enough socket connections, you might see long latencies. And the last part is about the BIOS, where you have to go when you're talking about 10 millisecond or 1 millisecond latency, and there hyper-threading in particular cases when you have, most of the time you will see gain, performance gain, throughput as well as response time. But if you have very contented locks, then the hyper-threading can actually increase your latency, and you may want to check by disabling it, is that causing it? If you, either you find first, do I have contented locks, or then HT could be causing you some trouble there. Prefetching, JVM is smart enough to do prefetching, and what we have seen nowadays, actually, we tune that working with both the JVM. JVM tend to do their own prefetching, and the hardware does prefetching. In the past, they were colliding. We have make sure that by default, those type of things should work fine. Now, next part would be, when you are talking about response time, there is particularly very low response time. You do need to know what kind of, and this is just one example I can give you here, that there are so many processor family just at the high level. For example, E7 series are 4-socket mission criticals. Then there is a E5 series, there are 3 type, and the E3 series entry level. If you are looking for the best response time, then the highest frequency parts are going to give you the best response time. And I try to highlight here, like E5 2600 series is the family which can give you the highest frequency part for the response time. So you do need to know there's no going away from, if you are going to go into the E7 series, then their frequencies tend to be less than the E5's 2-socket series. So you might see better response time with E5 2600 series. Another one is just example here. Even in the 2600 series, look at the middle column. You could almost be from the top frequency part, 2.9 gigahertz, to very low 1.8. And this frequency is going to directly impact your response time. And many times we have seen volume usually are from 2670 or 2665, which is almost 2 or 3 bin down. But if you are very sensitive, then there is not going away from the top bin parts. It all depends how critical it is. I would like to make one more comment. I have seen turbo frequency. How many people have heard about the turbo boost or turbo frequencies? Okay, so that's the interesting one. Nowadays we are going like 15-20% higher, so that means you could have got that much better response time. What really happens, the power management I talked about many times, when people are sensitive, they go disable the power management because they want a constant frequency. What happens with the constant frequency, you lose the turbo benefit. But there are a methodology where you could have both. You could let your system run at constant speed and could benefit from turbo. So if you are really care for the response time, you may want to look into it. Let me share one data point here. So this is a part with 8 core, and we try to see the scaling on the response time. What happens when we are using all 8 core versus 4 core? So as Daryl mentioned earlier, the benchmark is scaling very well. That you could see from 4 core to 8 core, you do twice on the throughput almost. One of the interesting thing you will not see in the median, almost no impact on the response time on the median. But look at the P99. The 8 core are able to hold the response time below 200 milliseconds for almost 50%, up to 50% of utilization there of the total load. While with the 4 core, in the very beginning itself, it goes above 200 milliseconds. So once you ensure scaling, with the more core, you will see the more benefit of the more core here on the response time. P99, again, if that is what you care for. The next one is leveraging your topology with the NUMA. Many of the nodes are NUMA. That means each processor has their own memory. And many times you are able to affinitize, other case times you are not able to affinitize due to different reasons. But there is a very clear benefit of the affinity. You can see on the top part, you can see more throughput, and median time, again, almost no impact. But if you look at the P99, there is very clearly for much longer, you could keep it below 500 millisecond and actually almost up to 25% below 100 millisecond range. So there are, once again, if you care for the P99 and we assume at the higher response time you do, when you want below 100 millisecond, then I guess the thing you need to look for is P99 values or even higher. Thank you.
Okay, so, oops. Right, so just a couple of points to close off here. So when you're looking at your system, let's say you're happy with it, the way that it's running right now, are there any signs that you can actually be achieving better performance than you actually are and getting better response than you actually are? So one sign would be, like we first talked about, you're not using very many threads there. So you basically have a fairly single-threaded application. So if you think that there is some parallelism there that you can exploit, then by all means do. And that may actually pay out as an improvement on your response time. If you have a lot of contended locks, that's something to keep an eye out for as well. There are lock monitor tools available that you can use for that. Look at your CPU utilization. If you think you're running full out and you look at your CPU utilization and it's only 60%, there's something there that's preventing you from fully saturating the CPU, and you got to get to the bottom of that because you're not using all the processing power that you can. And also, if you're spending a lot of time in the kernel, there's got to be some reasons for that too. It could be paging, it could be locking, other reasons as well. But if you're, let's say, more than 10% in the kernel, then there's some issue there that you should probably get to the bottom of. Lots of tools available as well. I just listed some of the ones that IBM provides here. So we certainly provide IBM Health Center. There are equivalent ones from Oracle as well. You can figure out what your JVM is doing, how well, where the hotspots are in that particular application, how your heap is performing. There's garbage collection analysis tools as well, ways of visualizing what's in your heap, what constitute the objects in your heap. You can find out, for example, if you do have an excessive object allocation problem. You look at your pause times, find out when they occur and what else was going on at that time. And then, of course, there's some offline tools as well that you can use to basically dump the contents of your heap at a certain time and then just paw through it to your heart's content and find out what's going on there. So that's all we had to say. So any questions on there? Go ahead. Well, I think it gets back to. I think it kind of depends on the situation that you're in there. It really, like I was saying about the frameworks, right? You really need to understand how to tune that particular framework and how your application is fitting into that, right? I don't know if there's actually a specific answer to that question. I think it really depends on. It's really a kind of a case by case. Maybe you can come up here. I can hardly hear you now. Maybe you can come up here afterwards. I can hardly hear you now, actually. Yes, sir.
The G1, is it G5?
You're talking about G1?
G1.
Are you talking about G1, the G1 garbage collector? I'm not sure what the question is. So the question is about, there's a Java 7 update 4, there's a GC that does not cause pause times. Okay, so he's talking about G1. I don't know anything about G1, to be honest with you. We're very, very little about it. But Dave up here can. Anything else? Yes, sir. Hyperthreading in GC? There you go.
So hyperthreading and GC should work fine because we have most of the JVMs had made sure there is no contention with respect to garbage collection part. So you will not see an issue with the hyperthreading and the garbage collection. Mostly it is somewhere else in your code. If you have a lot of contented log, then you could see the problem. So if there are any special case, we can try to run and see. So you can send, my contact was there, anil.kumar@intel.com, or if you have a card, feel free, I can. But no, I'm not aware of the concurrent with the hyperthreading having any issues, but you never know. But if they're sure, if you write to us, we can try to replicate it and see what can be done. Go ahead. There should not be a problem. Right? You said you can't go any more than 1.5 gig.
I can't go beyond 2 gigs. That's it. I have 3 things for so I guess like running the latest JVM.
Are you using the hotspot J9? That will be your guy there. He is the hotspot guy.
You can also talk about whatever your particular domain, like whatever your system is actually doing. We can discuss that afterwards if you like. Anything else? Okay, thank you, everyone.